Alright, let's do a little introduction to the theory of special relativity. First off, everything is relative. Everything depends on where you are. So here's me, and there's a millionaire beside me, and he looks at me and he says, he's poor. But over here, there's a billionaire standing beside him, and he looks at the millionaire and says, he's poor. Yes? So, how you describe other people and how much money they have depends on how much money you have yourself. So, in physics, the frame of reference is very, very important, and we must clearly identify the frame of reference in all the questions that we'll be doing in this unit, to be very careful about where you are observing different events from. There are two types of frames of reference in this unit. Inertial frames of reference. Sometimes Newton's laws work, sometimes they don't. Frames of reference in which Newton's laws of motion are observed are called inertial frames. For instance, the surface of the Earth is an inertial frame of reference. Newton's laws, mechanics, velocity, distance, time, all seem to work in this frame of reference. An inertial frame of reference is one in which it has a constant velocity, or even v is 0. And we'll look at another example of that in a second. A non-inertial frame of reference, measurements made with respect to some other frames of reference, Newton's laws appear to be violated. So, for example, when a bus goes around the corner, let's pretend that the bus had no windows, and there's a man inside, and he is holding on to a rail, and the bus goes around the corner, and he doesn't know that it's gone around the corner. Suddenly, he just starts to accelerate to the side. That would be Newton's laws not being followed. So, if you, and here's another one, if we try and throw and catch balls on a merry-go-round, and we watched a video of this, you'll also observe apparent violations of Newton's laws. Non-inertial frames of reference are ones that are accelerating. So as soon as a frame of reference is accelerating, we have problems. We're going to be sticking with this one up here. Yes? A frame of reference that moves with a constant velocity with respect to an inertial frame of reference is also an inertial frame of reference. So here's an example. Newton's laws work in the physics lab, which is on the Earth. Therefore, they also work in a train moving with a constant velocity with respect to the Earth. So all of these things have constant velocity, so they all are all inertial frames of reference. Principle of relativity. For all inertial frames of reference, the laws of Newtonian mechanics are the same. So Newton's laws work in all of these cases. Now, as we move into look more at relativity and modern physics, these experiments are hard to perform. So instead, scientists often do a thought experiment, which is a mental exercise used to investigate the potential consequences of a hypothesis. And this is Sheldon and Raj. Sheldon and Raj were trying to perform a thought experiment there. They were thinking about it. They didn't get up and do an experiment like Leonard would. Leonard is an experimental physicist. Sheldon is a theoretical physicist. He performs thought experiments. Now, as we move further into this unit, there are two facts or postulates that we need to keep in mind. Sometimes they're called Einstein's postulates. The first one we've kind of already covered. The laws of physics hold true for all inertial frames of reference. Yeah. So, for example, one example that caused Einstein to come up with this, if I have a rod and I have a coil of wire and current is running through it. If I put the rod into the coil, or if I move the coil up around the rod, it's the same thing. So the laws of physics hold true for all inertial frames of reference. It doesn't matter which one we talk about. These have to be identical. I should get the same results no matter what. Now the next postulate, we have to perform a thought experiment. Here is me, and I have a ball, and here's a student that I teach that I don't like, and I throw the ball at the student. How fast is the ball going when it hits the student? It's going at the velocity of the ball. That's how fast it will be going when it hits the student. You'll understand what I'm doing. Now I'm on top of a car that's moving this way with some velocity. Car. How fast will the ball hit this student? Now, here, the velocity would be equal to the velocity of the car plus the velocity that I throw the ball at. I would have to add them together here. Next one. It's me on top of a car with a flashlight. The velocity of the car is half the speed of light, so I'm moving very quickly. And I have my flashlight, and I shine a little bit of light, little bundle of light, a photon, turn it on and off super quick, and the light travels and hits the student in the eye. How fast is the light going when it hits this person? And the answer to that is C. The speed of light is a max. Speed of light is the speed of light in all frames of reference. I can't go faster than the speed of light. Light can't go faster than the speed of light. Light can't go slower than the speed of light. The speed of light is the speed of light, and it's a max. Okay? And so the second postulate is the speed of light is measured as constant in all frames of reference. This is a little trickier, but it's important as we move forward that we realize that the speed of light is always the speed of light.